Welcome, dear listener, to a gentle exploration of the scientific world. Tonight, we'll drift through ideas, discoveries, and wonders that have shaped our understanding of life and the universe. Whether you're lying in bed or simply letting your mind wander, I'm glad you're here. Feel free to let me know where in the world you're listening from and what time it is there. Are we both surrounded by silence and stars, or is the sun just beginning to rise in your sky? If these quiet, thoughtful journeys into science bring you peace, I'd love for you to subscribe. There are many more discoveries waiting just beyond the horizon. For most of human history, we assumed that gravity was the dominant force shaping the cosmos on the largest scales. After all, gravity pulls things together. It's what keeps your feet on the ground, the moon orbiting Earth, and stars clustered in galaxies. So naturally, scientists expected that the universe's expansion, which began with the Big Bang, would gradually slow down over time as gravity worked to pull everything back together. It made perfect sense, really. Imagine throwing a ball into the air. It starts fast, but gravity slows it down until it eventually falls back to Earth. The universe, we thought, should behave similarly. The initial explosive expansion of the Big Bang should gradually decelerate as gravity worked to pull all that matter back together. But the universe, as it often does, had other plans. In the late 1990s, two independent teams of astronomers were studying distant supernovae, stellar explosions so bright they can outshine entire galaxies. These particular supernovae, called type Ia supernovae, are wonderfully useful for astronomers because they all explode with roughly the same brightness, making them excellent cosmic lighthouses for measuring distances across the universe. The teams expected to find that these distant supernovae were brighter than predicted, which would indicate that the universe's expansion was slowing down as gravity worked against it. Instead, they found something completely unexpected. The supernovae were dimmer than expected, meaning they were farther away than they should be if the expansion was decelerating. The implications were staggering. Not only was the universe's expansion not slowing down, it was actually speeding up. Something was working against gravity on cosmic scales, stretching space itself at an accelerating rate. This discovery was so surprising, so fundamentally paradigm-shifting, that it earned the researchers the 2011 Nobel Prize in Physics. But what could possibly be causing this accelerated expansion? The answer, if we can call it that, is dark energy, a mysterious component that makes up roughly 68% of the total energy density of the universe. Think about that for a moment. More than 2/3 of everything that exists is composed of something we don't understand, something invisible and intangible that nonetheless shapes the fate of every galaxy, every star, every planet in the cosmos. The name dark energy is admittedly rather ominous, but it's not dark in the way a shadow is dark. It's called dark simply because it doesn't emit, absorb, or reflect light in any way we can detect. It's invisible to all our instruments, yet its effects permeate every cubic centimeter of space. It's rather like trying to study the wind by watching leaves dance. You can't see the wind itself, but its presence is undeniable. What makes dark energy even more peculiar is how it behaves. Unlike matter, which becomes more diluted as space expands, dark energy appears to maintain a constant density throughout the universe. As space stretches, more dark energy seems to appear to fill the new volume, maintaining that steady, relentless pressure that drives cosmic acceleration. Imagine inflating a balloon, but instead of the air inside becoming thinner as the balloon expands, new air mysteriously appears to maintain the same pressure. That's essentially what dark energy does to the fabric of space-time itself. The more the universe expands, the more dark energy there is to drive further expansion, creating a kind of cosmic feedback loop. This has profound implications for the future of our universe. In the early cosmos, when galaxies were closer together and matter was denser, gravity was the dominant force. But as the universe expanded and matter became more spread out, dark energy began to take over. We now live in what cosmologists call the dark energy-dominated era, and this dominance will only grow stronger with time. Billions of years from now, if dark energy continues to behave as it does today, the expansion will have stretched space so much that distant galaxies will disappear beyond our cosmic horizon. The night sky will grow darker and lonelier as fewer and fewer stars remain visible. Eventually, even nearby galaxies will drift away, leaving our own Milky Way isolated in an ever-expanding ocean of darkness. But we're getting ahead of ourselves. Right now, in this cosmic moment, dark energy is simply the universe's way of ensuring that space itself has room to breathe, room to grow. It's the gentle but inexorable force that gives the cosmos its grandest rhythm. Not the violent explosion we might imagine, but a slow, steady, almost meditative expansion that's been going on for billions of years and will likely continue for billions more. Scientists have proposed various explanations for what dark energy might be. Some suggest it's the energy of empty space itself, quantum fluctuations in the vacuum that create a kind of cosmic pressure. Others propose that our understanding of gravity breaks down on the largest scales, and what we call dark energy is really just a sign that we need new physics. Still, others wonder if dark energy is actually a new kind of field permeating space, similar to the fields that give particles their mass. The truth is, we simply don't know yet. Dark energy remains one of the greatest mysteries in modern science. A humble reminder that for all our technological prowess and theoretical sophistication, the universe still holds secrets that can surprise us, challenge us, and fill us with wonder. And perhaps that's exactly as it should be. In a cosmos where most of what exists is invisible and mysterious, where the very fabric of space is being gently stretched by forces we can barely comprehend, there's something profoundly beautiful about our small place in this vast, expanding tapestry. We are, quite literally, riding the cosmic expansion, participants in the universe's greatest ongoing story. So tonight, as you settle into sleep, remember that you're resting on a planet that's part of a galaxy, that's part of a universe that's slowly, quietly, majestically expanding into the infinite darkness. Dark energy, that mysterious cosmic gardener, is tending to space itself, ensuring there's always room for new possibilities, new discoveries, new dreams. The universe is growing larger with every breath you take, every heartbeat, every gentle thought that drifts through your mind as you drift towards sleep. And in that expansion, in that endless becoming, there's something almost comforting. A reminder that the cosmos itself is alive, dynamic, and full of mysteries still waiting to be discovered. Sleep well, fellow traveler. Tomorrow, the universe will be just a little bit larger than it is tonight, and dark energy will continue its patient work of writing the future across the stars. The universe has given us its greatest secret. It's not standing still. Every galaxy, every star, every wisp of cosmic dust is moving, shifting, evolving in ways we're only beginning to understand. But there's something else happening, something that challenges everything we thought we knew about the cosmos. The expansion of the universe isn't slowing down as we once expected. It's speeding up. Welcome back to another gentle journey through the cosmos. If you're settling in for the evening, perhaps with a warm cup of tea, or simply letting the day's worries fade away, you've found the right place. Tonight, we're exploring one of the most profound mysteries in all of science, dark energy, the invisible force that's not just expanding our universe, but accelerating that expansion at an ever-increasing pace. Before we drift into this cosmic mystery together, I'd love to know where in the world you're listening from tonight. Are you watching the same stars that ancient astronomers once puzzled over? Drop a comment below and let me know your corner of the globe. And if this journey into the unknown brings you a sense of wonder or peace, A gentle like or subscribe helps these cosmic stories reach other curious minds seeking a moment of scientific serenity. Now, I do hope this exploration isn't so fascinating that it keeps you awake, but if it does, at least you'll understand a bit more about the force that's quietly reshaping the entire universe while you sleep. So settle in, let your breathing slow, and prepare to discover why the cosmos is not just vast, but getting vaster every moment. Let's begin our journey into the realm of dark energy, where the very fabric of space itself holds secrets we're only just beginning to glimpse. For most of human history, we've looked up at the night sky and seen constancy. The stars seemed fixed, eternal, unchanging markers in the cosmic dark. Even when we discovered that the universe was expanding, thanks to Edwin Hubble's groundbreaking observations in the 1920s, we assumed this expansion would gradually slow down. After all, gravity should be pulling everything back together, shouldn't it? It seemed only logical that the universe, having burst forth in the Big Bang, would eventually exhaust its initial momentum and begin to decelerate. This wasn't just scientific intuition, it was backed by solid reasoning. Imagine throwing a ball into the air. No matter how hard you throw it, gravity will eventually slow it down, stop it, and pull it back to Earth. We thought the universe worked the same way. The gravitational attraction between all the matter in the cosmos should act like a cosmic brake, gradually slowing the expansion until it either stopped entirely or even reversed, leading to a big crunch where everything collapsed back into a single point. But the universe, as it often does, had other plans. In the late 1990s, two independent teams of astronomers were studying distant supernovae, using these stellar explosions as cosmic lighthouses to measure how the expansion of the universe had changed over time. What they expected to find was evidence of this gradual deceleration. What they actually discovered turned cosmology on its head. The distant supernovae appeared dimmer than they should have if the universe's expansion were slowing down. This could only mean one thing. The expansion wasn't decelerating at all. It was accelerating. The universe wasn't just growing larger, it was growing larger at an ever-increasing rate, as if some invisible force were pushing everything apart with greater and greater strength as time went on. This discovery was so unexpected, so contrary to our understanding of physics, that the scientific community initially met it with skepticism. Surely there was an error in the measurements, or perhaps dust between distant galaxies was making the supernovae appear dimmer than they actually were. But as more observations poured in, the evidence became undeniable. The universe's expansion was indeed accelerating, and had been for billions of years. To explain this cosmic acceleration, scientists had to propose the existence of something entirely new: dark energy. The name itself reflects our profound ignorance about this phenomenon. We call it dark, not because it absorbs light, but because we can't see it, detect it directly, or even understand what it is. We only know it exists because of its effects on the expansion of space itself. Dark energy is unlike anything else we know in the universe. While matter, both ordinary and dark, tends to clump together under the influence of gravity, dark energy appears to be smoothly distributed throughout space. It doesn't form structures, doesn't interact with light, and doesn't seem to be affected by the presence of matter. Instead, it acts as a kind of anti-gravity, pushing space apart rather than pulling it together. What makes dark energy even more mysterious is its apparent constancy. As the universe expands and the density of matter decreases, dark energy's density appears to remain the same. This creates a cosmic feedback loop. As space expands, there's more space for dark energy to fill, which means more dark energy to drive the expansion, which creates even more space, and so on. It's as if the universe has discovered a way to create more of the very thing that's driving its expansion. The implications of this discovery extend far beyond academic curiosity. Dark energy appears to make up about 68% of the total energy content of the universe. Combined with dark matter at about 27%, this means that everything we can see and touch, all the stars and galaxies and planets, all the ordinary matter that makes up our bodies and our world, accounts for less than 5% of the universe. We live in a cosmos dominated by invisible, poorly understood forces. This cosmic acceleration also determines the ultimate fate of our universe. In a universe dominated by dark energy, the expansion will continue forever, with galaxies moving farther and farther apart. Eventually, distant galaxies will recede so fast that their light will no longer be able to reach us. The observable universe will shrink, not because space is contracting, but because the expansion is carrying distant light sources beyond our cosmic horizon. In the far future, inhabitants of the Milky Way might look out into a night sky containing only the galaxies in our local group, with the rest of the universe having disappeared into the accelerating darkness. But what exactly is dark energy? Despite decades of research and observation, we still don't know. It could be the energy of empty space itself, a quantum mechanical phenomenon where even the vacuum of space contains a subtle but persistent energy that drives expansion. It could be a new fundamental field, similar to the fields that give particles their mass, but operating on cosmic scales. Or it could be a sign that our understanding of gravity itself breaks down on the largest scales, requiring new physics to explain what we observe. Some researchers have proposed that dark energy might not be constant after all. Perhaps it's a dynamic field that changes over time, sometimes accelerating the expansion, sometimes slowing it down. Others suggest that what we interpret as dark energy might actually be evidence that we live in a higher dimensional space, where the familiar three dimensions of space and one of time are embedded in a larger geometric structure that affects how gravity behaves over cosmic distances. The search for answers continues. New telescopes and surveys are mapping the expansion history of the universe in unprecedented detail, looking for clues about the nature of dark energy. Scientists are measuring how the acceleration has changed over cosmic time, searching for patterns that might reveal the underlying physics. They're also looking for alternative explanations, ways to account for the observed acceleration without invoking a mysterious new form of energy. What we do know is that dark energy represents one of the most profound puzzles in modern science. It's a reminder that for all our technological sophistication and scientific understanding, the universe still holds secrets that challenge our most basic assumptions about reality. The cosmos is not just stranger than we imagine, it may be stranger than we can imagine. As you drift off to sleep tonight, consider this. The space between you and the nearest star is slowly, imperceptibly expanding. The distance between galaxies is growing larger with each passing moment, driven by a force we can't see, can't touch, and don't understand. Dark energy is working its subtle influence even now in the quiet of your room, gently stretching the fabric of space-time itself. It's a humbling thought, really. We've learned to split atoms, to sequence genomes, to send messages instantly across the globe. We've walked on the moon and sent probes to the edge of the solar system. Yet the largest component of our universe remains a complete mystery to us, a dark energy that shapes the cosmos in ways we're only beginning to glimpse. And perhaps that's exactly as it should be. In a universe where dark energy reigns supreme, where invisible forces drive the grandest processes we know, there's still room for wonder, still space for questions, still mysteries waiting to be solved. The accelerating expansion of space ensures that the universe will always have more secrets to reveal, more puzzles to ponder, more gentle mysteries to contemplate as we drift through the cosmic dark. So sleep well, knowing that the universe around you is vast, dynamic, and full of invisible wonders. Dark energy may be mysterious, but it's also a reminder that reality is far richer and more complex than our everyday experience suggests. In the morning, when you wake, you'll be in a universe that's slightly larger than it was when you fell asleep, stretched by forces we're still learning to understand, shaped by energies that work in silence and darkness, creating the cosmic stage on which all of existence unfolds. The universe is expanding, accelerating, evolving, and we're along for the ride, curious passengers on a cosmic journey powered by the most mysterious force in existence. What a magnificent mystery to fall asleep to. What a wondrous puzzle to dream about. What a beautiful reminder that the cosmos still has so much more to teach us. Walking through the cosmos of dark energy, we arrive at a realm where the very fabric of space itself becomes mysterious. We've seen how the universe began with a Big Bang, how galaxies formed and danced together, and how time itself can bend and stretch like cosmic taffy. But now we must confront perhaps the most profound puzzle of all. Something invisible, something powerful, something that makes up more than 2/3 of everything that exists, yet remains completely unknown to us. Dark energy is the universe's greatest secret, a force so subtle we can barely detect it, yet so powerful it's driving the entire cosmos apart. Imagine, if you will, that you're watching a fireworks display, but instead of the sparks falling back down to Earth, they begin accelerating outward, faster and faster, defying gravity and common sense. That's essentially what our universe is doing right now, and dark energy is the mysterious force behind this cosmic acceleration. For most of human history, we assume the universe was either static and unchanging, or if it was expanding, that expansion should be slowing down. After all, if you throw a ball into the air, gravity pulls it back down. If the universe began with a Big Bang, shouldn't gravity be pulling everything back together, gradually slowing the expansion until it stops? This seemed like basic physics, as natural as breathing. But in the 1990s, two independent teams of astronomers were studying distant supernovae, those brilliant stellar explosions that can outshine entire galaxies. These particular supernovae, called Type 1a, are wonderfully consistent in their brightness, making them excellent cosmic lighthouses. By measuring how bright they appear from Earth and comparing that to how bright they should be, astronomers can calculate their distance with remarkable precision. What these teams discovered was shocking. The distant supernovae, those from billions of years ago, appeared dimmer than expected. This meant they were farther away than they should have been if the universe's expansion was slowing down. Instead of decelerating, the universe's expansion was accelerating. It was as if that ball you threw into the air suddenly started speeding up as it climbed higher. This discovery earned the 2011 Nobel Prize in Physics, but it also created the biggest mystery in modern cosmology. What could possibly be causing this acceleration? The answer, or rather the name we gave to our ignorance, is dark energy. It's called dark not because it's sinister, but because it doesn't emit, absorb, or reflect light. It's invisible to all our instruments, detectable only through its gravitational effects on the cosmos. Dark energy makes up approximately 68% of the total energy content of the universe. Let that sink in for a moment. More than 2/3 of everything that exists is something we don't understand. It's as if you discovered that most of your house was made of invisible rooms you'd never seen, filled with furniture you couldn't touch, yet somehow keeping the whole structure standing. What makes dark energy so peculiar is how it behaves. Unlike matter, which gets more diluted as space expands, dark energy appears to maintain a constant density. As the universe grows larger, there's more dark energy, not less. It's like having a magical ink that when you add water to dilute it, somehow becomes more concentrated instead of weaker. This creates a feedback loop. More space means more dark energy, which drives faster expansion, which creates even more space, and so on. This constant density is what makes dark energy so different from anything we're familiar with. If you have a box of gas and you double the size of the box, the gas density drops by half. But if you filled that box with dark energy and doubled its size, you'd somehow end up with twice as much dark energy, maintaining the same density as before. It's a property so strange that it challenges our basic understanding of how energy and matter behave. The implications are staggering. If dark energy continues to dominate the universe's expansion, and if its density remains constant as space grows, then the cosmos faces a rather lonely future. Galaxies, not gravitationally bound to our local group, will eventually recede so far that their light will no longer reach us. The night sky will grow darker and darker as distant galaxies fade from view, stretched beyond the cosmic horizon by the relentless expansion of space. But what is dark energy exactly? The honest answer is that we don't know. We have several theories, each more speculative than the last. One possibility is that dark energy is simply the energy of empty space itself, what physicists call vacuum energy. According to quantum mechanics, even empty space is never truly empty. It's filled with virtual particles popping in and out of existence, creating a kind of quantum foam that might exert a repulsive force. The problem with this idea is that when physicists calculate how much energy empty space should have, they get a number that's either 0 or approximately 10 to the power of 120 times larger than what we observe. This has been called the worst prediction in the history of physics. It's like predicting that a teacup will weigh as much as a mountain, then discovering it weighs exactly what you'd expect a teacup to weigh. Another possibility is that dark energy is a new type of field, similar to the fields that give particles their mass or carry electromagnetic forces. This hypothetical field, sometimes called quintessence, would permeate all of space and have the unusual property of creating a repulsive gravitational effect. Unlike the cosmological constant, quintessence could change over time, potentially offering a more dynamic explanation for cosmic acceleration. Some physicists have proposed that dark energy might not be a thing at all, but rather a sign that our understanding of gravity itself is incomplete. Perhaps Einstein's general relativity, which has passed every test we've thrown at it for over a century, breaks down on cosmic scales. Maybe gravity behaves differently when acting across billions of light years, becoming repulsive rather than attractive under certain conditions. There's also the possibility that we're misinterpreting the data entirely. Perhaps the universe isn't actually accelerating, but appears to be due to some other effect we haven't considered. Maybe we're living in an unusual region of space, or maybe light behaves differently over cosmic distances than we think. These explanations are less popular among cosmologists, but they remain possibilities. The search for dark energy has spawned some of the most ambitious scientific projects in human history. Telescopes like the Dark Energy Survey and the upcoming Euclid mission are mapping billions of galaxies, measuring their distances and studying how cosmic structures have evolved over time. By creating incredibly detailed maps of the universe at different epochs, astronomers hope to understand how dark energy has influenced the growth of galaxies and the expansion of space. One of the most promising approaches involves studying something called baryon acoustic oscillations, essentially fossilized sound waves from the early universe. These oscillations left subtle patterns in the distribution of galaxies, patterns that can be used as a standard ruler to measure cosmic distances. By tracking how these patterns have changed over time, astronomers can chart the history of cosmic expansion and potentially understand what's driving it. Another approach focuses on weak gravitational lensing, the subtle distortion of distant galaxy shapes caused by the gravitational influence of intervening matter. By studying these tiny distortions, astronomers can map the distribution of both visible and dark matter throughout the universe, potentially revealing clues about the nature of dark energy. The stakes couldn't be higher. Understanding dark energy isn't just an academic exercise, it's the key to understanding the ultimate fate of the universe. If dark energy continues to dominate, the cosmos will expand forever, eventually becoming cold, dark, and empty. If it weakens or changes character, the universe might recollapse in a big crunch or undergo some other dramatic transformation we can't yet imagine. Perhaps most humbling of all is the realization that dark energy represents a fundamental gap in our knowledge. We've mapped the human genome, split the atom, and sent robots to Mars, yet we remain completely ignorant about the dominant component of our own universe. It's a reminder that for all our technological prowess and scientific sophistication, we're still cosmic infants, taking our first tentative steps toward understanding the vast, mysterious cosmos we inhabit. Dark energy whispers to us from the depths of space, a gentle but persistent voice reminding us that the universe is far stranger and more wonderful than we ever imagined. It's a force that works in darkness, shapes galaxies, and determines the fate of everything that exists. And yet, despite its cosmic importance, it remains as mysterious as a dream, as elusive as morning mist, as unknowable as the thoughts of stars. In the end, dark energy serves as both a scientific challenge and a philosophical meditation. It reminds us that the cosmos is not just larger than we know, but larger than we can know, at least for now. It's a humbling thought, but also an inspiring one, because it means there are still profound mysteries waiting to be solved, still cosmic secrets waiting to be whispered to those patient enough to listen to the silence between the stars. Welcome back to The Sleepy Scientist, where the mysteries of the cosmos unfold gently in the quiet hours, and curiosity finds its way to rest. Tonight, we're embarking on a journey through one of the universe's most profound puzzles, a force so mysterious that it makes up nearly 70% of everything that exists, yet remains completely invisible to us. Before we drift into this cosmic mystery together, I'd love to know where you're listening from tonight and what time it is in your corner of the world. There's something beautifully fitting about exploring the expanding universe while we're all scattered across different time zones, each of us finding our way to this moment of wonder. If you find tonight's gentle exploration soothing, perhaps consider giving this video a like or subscribing to join our growing community of sleepy stargazers. It helps other curious minds discover these quiet, cosmic journeys. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll drift off knowing something extraordinary about the very fabric of reality itself. So settle in, let your breathing slow, and prepare to contemplate the invisible force that's stretching the universe itself. We call it dark energy, and it might just be the strangest thing we've never seen. Picture, if you will, the universe as a vast balloon, stretching in all directions, carrying galaxies like specks of dust on its surface. But here's what's truly remarkable. This balloon isn't just expanding, it's expanding faster and faster, as if some invisible hand were continuously adding more air, more space, more distance between every point. This is the reality we inhabit, a universe in accelerated expansion, driven by something we can barely comprehend. Dark energy isn't just a footnote in cosmic history. It's the dominant force shaping everything we see and everything we don't see. It outweighs all the matter in the universe, all the stars, planets, and galaxies combined by more than 2 to 1. Yet, we know almost nothing about it. The story of dark energy's discovery begins, as many great scientific revelations do, with scientists expecting one thing and finding something entirely different. In the 1990s, 2 teams of astronomers set out to measure how the expansion of the universe was slowing down. After all, logic suggested that gravity, pulling everything together, should be gradually applying the brakes to cosmic expansion. They studied supernovae, those spectacular stellar explosions that serve as cosmic lighthouses, each one shining with roughly the same brightness. By comparing how bright these explosions appeared to how bright they should appear at different distances, astronomers could map the expansion history of the universe with unprecedented precision. What they found changed everything. The universe wasn't slowing down at all. It was speeding up. The expansion was accelerating, as if some mysterious force were pushing against gravity itself, stretching space faster and faster as time went on. It was like throwing a ball into the air and watching it accelerate upward instead of falling back down. This discovery was so unexpected, so contrary to theoretical predictions, that both teams spent months checking and rechecking their data. Surely there had to be an error. Surely the universe couldn't be behaving so strangely. But the evidence was undeniable. In 1998, they announced their findings to the world, and cosmology would never be the same. The force driving this acceleration was dubbed dark energy, not because it's literally dark, but because it's invisible, undetectable, except through its gravitational effects on the largest scales. It doesn't emit light, doesn't absorb light, doesn't interact with matter in any way we can directly observe. It's like a ghost haunting the cosmos, felt but never seen. But what exactly is dark energy? The honest answer is that we don't know. It's one of the deepest mysteries in modern physics, a reminder that for all our scientific progress, the universe still holds secrets that humble our understanding. The simplest explanation, proposed by Einstein himself decades before dark energy's discovery, is something called the cosmological constant. Einstein imagined empty space itself possessing an inherent energy, a kind of springiness that pushes outward. He originally introduced this concept to balance the attractive force of gravity and create a static universe, but he later abandoned the idea when evidence for cosmic expansion emerged. Now, it seems Einstein's discarded concept might have been prescient after all. If empty space carries energy, and if that energy remains constant even as space expands, then as the universe grows larger, there's more empty space and therefore more of this repulsive energy. It's a force that strengthens as the universe stretches, providing exactly the kind of acceleration we observe. Yet this explanation brings its own puzzle. When physicists try to calculate how much energy empty space should contain based on quantum mechanics, they get an answer that's wrong by a factor of 10 to the power of 120. That's not just wrong, it's spectacularly, embarrassingly wrong, perhaps the worst prediction in the history of science. So while the cosmological constant might explain dark energy's behavior, it doesn't explain why it has the value it does, or why it's not vastly larger than observed. It's like solving one mystery only to uncover an even deeper one. Other theories propose that dark energy isn't constant at all, but rather a dynamic field that changes over time. This hypothetical field, sometimes called quintessence after the fifth element of ancient philosophy, would permeate all of space like an invisible fluid, its properties evolving as the universe ages. Quintessence could explain why dark energy's effects became dominant relatively recently in cosmic history. For billions of years after the Big Bang, matter and radiation were dense enough that gravity dominated, slowing the expansion. But as the universe grew and matter became more dilute, dark energy's influence grew stronger, eventually taking control and accelerating the expansion. Still, other theories suggest that dark energy might not be a thing at all, but rather a sign that our understanding of gravity itself is incomplete. Perhaps Einstein's theory of general relativity, so successful at describing gravity on smaller scales, breaks down when applied to the entire universe. Perhaps there are extra dimensions we can't perceive, or modifications to gravity that only become apparent across cosmic distances. These ideas push the boundaries of physics, suggesting that the universe operates by rules we haven't yet discovered. They're speculative, certainly, but then again, So was the very idea of cosmic acceleration until we found evidence for it written in starlight. What makes dark energy particularly mysterious is how perfectly it seems calibrated for our existence. If dark energy were much stronger, it would have dominated the universe's expansion from the very beginning, preventing galaxies, stars, and planets from forming. The universe would be a cold, empty void, devoid of the complex structures that make life possible. If dark energy were much weaker, or if it didn't exist at all, the universe might have collapsed back in on itself long ago, ending in a big crunch rather than continuing to expand. Again, no time for complexity, no opportunity for consciousness to emerge and contemplate its own cosmic context. Instead, dark energy has just the right strength to allow billions of years of cosmic evolution while still driving the current acceleration. It's as if the universe were fine-tuned for both structure formation and ultimate expansion, a cosmic balancing act of breathtaking precision. This apparent fine-tuning is both fascinating and troubling for physicists. Is it evidence of design? Of multiple universes where only the ones with suitable dark energy give rise to observers like us? Or is there some deeper principle we haven't yet grasped that explains why the universe's properties are what they are? As we contemplate these questions, we're forced to confront the limits of human knowledge. Dark energy reminds us that we inhabit a universe far stranger and more mysterious than our ancestors ever imagined. We are pattern-seeking creatures living in a cosmos dominated by something we cannot see, touch, or directly study. Yet this mystery isn't cause for despair, but for wonder. Every night, as you look up at the stars, you're witnessing the handiwork of dark energy. Every galaxy you glimpse through a telescope is being carried away by this invisible force, space itself stretching between us and distant worlds. The very fact that we can detect dark energy's influence, that we can measure its effects, and ponder its nature, is itself remarkable. We are matter contemplating the force that shapes matter's cosmic destiny, consciousness arising from atoms to wonder about the energy that governs atoms' ultimate fate. Future telescopes and experiments may reveal dark energy's secrets. We may discover new particles, new fields, new dimensions of reality that explain this cosmic acceleration. Or we may find that dark energy is something even stranger than we currently imagine, something that requires entirely new frameworks for understanding the universe. Until then, we live in a time of cosmic mystery, inhabitants of an accelerating universe driven by forces we can barely comprehend. It's humbling and exhilarating in equal measure, a reminder that reality extends far beyond the boundaries of human experience. So as you settle into sleep tonight, carried by the gentle rhythm of your breathing, remember that you too are part of this cosmic expansion. The space between your atoms, the distance between your thoughts and the stars, all of it shaped by the invisible hand of dark energy. The universe is stretching, growing, evolving in ways that dwarf human timescales and human understanding. And yet here you are, a temporary arrangement of stardust and consciousness, able to contemplate the very forces that govern your cosmic home. Sleep well, fellow traveler in this expanding cosmos. Dark energy will continue its patient work while you rest, stretching space, carrying galaxies toward an uncertain future, writing the universe's destiny in a language we're only beginning to learn to read. In the vast expanse of the cosmos, where galaxies spiral through darkness like cosmic pinwheels, there exists a force so mysterious that it makes up more than 2/3 of everything that exists, yet remains completely invisible to our eyes. Dark energy, as scientists have named it, is the universe's most elusive secret, quietly driving the accelerating expansion of space itself while we sleep peacefully beneath the stars. Tonight, as you settle into your blankets and let your thoughts drift toward rest, imagine this. Every second that passes, every breath you take, The universe around you is growing larger. Not just the objects in it moving apart, but space itself stretching like an invisible fabric being pulled in all directions. And the force responsible for this cosmic inflation is something we can neither see nor touch, something that challenges everything we thought we knew about the nature of reality. The story of dark energy begins not with telescopes or equations, but with expectations. For most of the 20th century, astronomers believed they understood the universe's trajectory. After the Big Bang, they reasoned, the expansion of space should be slowing down, like a ball thrown into the air that eventually succumbs to gravity and falls back to Earth. The gravitational pull of all the matter in the universe, they thought, would act as a cosmic brake, gradually decelerating the expansion until it perhaps even reversed, leading to a big crunch where everything would collapse back into a single point. It was a tidy, logical picture. Gravity, the force that keeps our feet on the ground and holds planets in their orbits, should surely be strong enough to rein in the universe's expansion. The only question was whether the universe contained enough matter to eventually halt the expansion completely, or whether it would slow down but continue expanding forever at an ever-decreasing rate. But the universe, as it often does, had other plans. In the 1990s, two independent teams of astronomers set out to measure the deceleration of cosmic expansion by observing distant supernovae. These stellar explosions, particularly type Ia supernovae, are remarkably consistent in their brightness, making them perfect cosmic lighthouses for measuring distances across vast stretches of space and time. The astronomers expected to find evidence of deceleration. Instead, they discovered something that shook the foundations of cosmology. The expansion of the universe wasn't slowing down at all. It was speeding up. The most distant supernovae appeared dimmer than expected, suggesting they were farther away than they should be if the universe's expansion had been constant or decelerating. Something was pushing space apart with increasing vigor, overcoming the gravitational attraction of all the matter in the universe. This discovery earned the 2011 Nobel Prize in Physics, but it also presented science with perhaps its greatest mystery. What could possibly be causing this acceleration? The answer, or rather the name given to our ignorance, is dark energy. It's called dark, not because it's sinister, but because it doesn't emit, absorb, or reflect light. It's essentially invisible to all our instruments, detectable only through its gravitational effects on the expansion of space itself. To understand just how mysterious dark energy is, consider this. It appears to make up about 68% of the total energy content of the universe. Dark matter, another mysterious component, accounts for about 27%. That means all the ordinary matter we can see, every star, planet, galaxy, and nebula, every atom in your body, represents less than 5% of the universe. We are, quite literally, living in a cosmos dominated by things we don't understand. Dark energy's properties are as puzzling as its existence. Unlike matter, which becomes more diluted as the universe expands, dark energy maintains a constant density. As space grows larger, more dark energy appears to fill it, maintaining the same amount of energy per cubic meter. This means that as the universe expands, the total amount of dark energy increases, providing an ever stronger push against the gravitational pull of matter. Imagine inflating a balloon, but instead of the air inside becoming less dense as the balloon expands, the air somehow maintains its density by creating more of itself. That's essentially what dark energy does to space. The larger the universe becomes, the more dark energy it contains, and the faster it expands. It's a runaway process that shows no signs of slowing down. The implications of dark energy's dominance are profound and, depending on your perspective, either thrilling or unsettling. For billions of years after the Big Bang, matter and radiation were the dominant forces in the universe. During this period, gravity was winning the cosmic tug-of-war, slowing the expansion and allowing matter to clump together into the first stars and galaxies. But as the universe expanded and matter became more dilute, dark energy's influence grew stronger. About 5 billion years ago, when our solar system was just beginning to form, dark energy finally overcame matter's gravitational influence and began accelerating the expansion. This marked a fundamental transition in the universe's evolution, from a matter-dominated cosmos to one ruled by dark energy. Since then, the acceleration has been increasing, and dark energy's grip on the universe has been tightening. What does this mean for the future? If dark energy continues to dominate, the universe will expand at an ever-increasing rate. Galaxies will recede from each other faster and faster until they disappear beyond each other's cosmic horizons. The night sky will gradually become darker as distant galaxies fade from view. Eventually, even nearby galaxies will be carried away by the expansion of space, leaving our own galaxy isolated in an expanding ocean of darkness. But the story doesn't end there. As expansion continues, even the stars within our galaxy will eventually burn out, leaving behind only cold, dark remnants. The universe will become a vast, cold, empty place, punctuated only by the occasional flash of a proton decay or the faint glow of Hawking radiation from evaporating black holes. It's a future that stretches across unimaginable timescales, where the warm, star-filled universe we know today will be remembered only as a brief, bright moment in cosmic history. Yet this far future, however melancholy it might seem, is still trillions of years away. For now, dark energy serves as a reminder of how much we still don't know about the universe we inhabit. It challenges our understanding of physics and forces us to confront the possibility that the cosmos operates according to principles we have yet to discover. Scientists have proposed several theories to explain dark energy's nature. One possibility is that it represents the energy of empty space itself, a concept that emerges from quantum field theory. According to this theory, even completely empty space is filled with quantum fluctuations, virtual particles that pop in and out of existence. These fluctuations should contribute a certain amount of energy to every cubic meter of space, creating a kind of cosmic pressure that could drive expansion. The problem with this explanation is that when physicists calculate how much energy these quantum fluctuations should contribute, they get a number that's about 10 to the power of 120 times larger than the observed value of dark energy. This discrepancy has been called the worst theoretical prediction in the history of physics. Either our understanding of quantum mechanics is fundamentally flawed, or dark energy has nothing to do with quantum fluctuations. Another possibility is that dark energy isn't a property of space itself, but rather a new kind of field, similar to the electromagnetic field, but with very different properties. This hypothetical field, sometimes called quintessence after the fifth element of ancient philosophy, would permeate all of space but interact so weakly with ordinary matter that we can't detect it directly. Unlike the cosmological constant, quintessence could change over time, potentially leading to different phases of cosmic evolution. Some physicists have suggested even more exotic explanations. Perhaps dark energy is a sign that our understanding of gravity itself is incomplete. Einstein's general relativity, while remarkably successful, might need modification on cosmic scales. Or perhaps dark energy is evidence of extra dimensions, hidden aspects of reality that we can't directly perceive, but that influence the behavior of space and time. There's also the intriguing possibility that dark energy is connected to the fundamental structure of space-time itself. Some theories suggest that space and time are not continuous, but are made up of discrete units, like pixels on a cosmic screen. If this is true, dark energy might be related to the energy required to create new units of space-time as the universe expands. The search for dark energy's true nature has spawned ambitious observational programs. Telescopes like the Dark Energy Survey and the upcoming Euclid space mission are mapping the distribution of galaxies across cosmic time, looking for subtle patterns that might reveal dark energy's properties. These surveys are essentially conducting archaeology on the universe itself, using the fossil light from distant galaxies to reconstruct the history of cosmic expansion. Ground-based experiments are also contributing to our understanding. The Dark Energy Spectroscopic Instrument, or DESI, is measuring the distances to millions of galaxies, creating the most detailed three-dimensional map of the universe ever constructed. By comparing how the universe looked at different times in its history, scientists hope to determine whether dark energy has remained constant or has evolved over time. But perhaps the most remarkable aspect of dark energy is what it tells us about our place in the cosmos. We live in a universe that is not only stranger than we imagine, but stranger than we can imagine. The very space around us is imbued with a mysterious energy that shapes the destiny of everything that exists. Every atom in your body, every star in the sky, every galaxy in the observable universe is caught up in dark energy's cosmic dance. As you drift towards sleep tonight, carried along by the gentle rhythm of your breathing, remember that you are also being carried along by the expansion of the universe itself. The space between the atoms in your body, the distance between Earth and the stars, the gaps between galaxies, all are growing larger with each passing moment, driven by a force that science has named but not yet understood. Dark energy reminds us that the universe is full of mysteries waiting to be discovered. It challenges us to remain humble in the face of cosmic immensity and to keep asking questions about the nature of reality. In a cosmos where most of what exists is invisible and unknown, perhaps the greatest wonder is not that we understand so little, but that we understand anything at all. The story of dark energy is still being written. Future generations of astronomers and physicists will undoubtedly uncover new clues about its nature, perhaps revealing connections to other mysteries of physics that we can't yet imagine. They may discover that dark energy is the key to understanding quantum gravity, or that it provides a window into parallel universes, or that it's something else entirely, something so strange and wonderful that we don't yet have words for it. Until then, we can only marvel at the fact that we live in a universe powered by invisible forces, a cosmos that continues to expand and evolve in ways that challenge our deepest assumptions about reality. Dark energy may be mysterious, but it's also a reminder that the universe is far more interesting and complex than we ever dared to dream. So as you close your eyes and let consciousness fade into the peaceful darkness of sleep, take comfort in knowing that you are part of something magnificent and mysterious. The same dark energy that drives the expansion of the universe flows through the space around you, connecting you to the deepest mysteries of existence. In the morning, when you wake to sunlight streaming through your window, remember that you have spent the night traveling through space on a planet orbiting a star in a galaxy that is itself rushing through an expanding universe, carried along by forces that science is only beginning to comprehend. The universe may be dark and mysterious, but it is also beautiful beyond measure, and you are an integral part of its unfolding story. Dream well, fellow traveler, as you journey through the darkness toward whatever revelations tomorrow may bring. Looking back through the vast mysteries we've explored together, we find ourselves at another crossroads in our cosmic journey. We've traveled from the birth of galaxies to the nature of time itself, and now we turn our attention to one of the universe's most enigmatic forces, dark energy. It's the invisible puppeteer pulling the strings of cosmic expansion, the silent conductor orchestrating the universe's accelerating dance into an ever colder, ever emptier future. As you settle in tonight, perhaps with a warm cup of tea or simply the quiet comfort of your own breathing, let's drift together into this deepest of mysteries. For dark energy is not just another cosmic curiosity, it's the dominant force shaping everything we see and everything we'll never see. It makes up more than 2/3 of all the energy in the universe, yet we know almost nothing about what it actually is. Imagine, if you will, that you've spent your entire life in a house and only now discovered that most of your home is made of rooms you've never seen, filled with furniture you can't touch, lit by lights that cast no shadows. That's where we find ourselves with dark energy. We know it's there because we can see its effects, but the thing itself remains as elusive as a whisper in an empty room. The story begins, as many cosmic stories do, with expectations that turned out to be beautifully, mysteriously wrong. In the 1990s, astronomers set out to measure how much the expansion of the universe was slowing down. After all, gravity should be pulling everything back together, right? The universe had exploded outward in the Big Bang, but surely, they reasoned, that initial burst of energy would gradually fade as gravity worked its patient, persistent magic. Two teams of researchers working independently turned their telescopes toward a particular type of stellar explosion called Type 1a supernovae. These cosmic lighthouses are wonderfully useful because they always explode with roughly the same brightness, making them reliable distance markers across the vastness of space. By measuring how bright they appear from Earth and comparing that to how bright they should be, astronomers can calculate how far away they are. And by analyzing the light itself, they can determine how fast the galaxy containing the supernova is moving away from us. The plan was elegant in its simplicity. Measure supernova at various distances, plot how fast they're receding, and see how much the expansion has slowed down over cosmic time. It should have been a straightforward confirmation of what everyone expected, gravity gradually winning its tug of war against the initial expansion. But the universe, as it so often does, had other plans. When the data came in, both teams found the same shocking result. The distant supernova were dimmer than expected. Not dimmer because something was blocking their light, but dimmer because they were farther away than they should have been if the expansion were slowing down. The universe wasn't just expanding, it was expanding faster and faster, accelerating like a car with the gas pedal pressed to the floor. This discovery earned the 1998 Nobel Prize in Physics, but it also created one of the biggest mysteries in all of science. Something was pushing the universe apart, something that worked against gravity on the largest scales. They called it dark energy, though the name tells us more about our ignorance than our understanding. It's dark not because it absorbs light, but because we can't see it directly. It's energy because it affects the expansion of space itself. Think of it this way. Imagine you're watching a film of an explosion, but instead of the debris slowing down as it spreads out, it keeps accelerating, flying apart faster and faster as time goes on. That's what we're seeing when we look at the universe. Galaxies aren't just moving away from each other. They're moving away faster now than they were billions of years ago. The implications are staggering. Dark energy makes up approximately 68% of all the energy in the universe. Dark matter, that other mysterious component we've touched on before, accounts for about 27%. That leaves ordinary matter, the stuff that makes up stars, planets, and people, accounting for less than 5% of everything. We are not just rare in the universe, we are made of the rare stuff in the universe. But what is dark energy? The honest answer is that we don't know, and that ignorance is both humbling and thrilling. There are theories, of course. The leading candidate is something called the cosmological constant, an idea that Einstein himself proposed and then abandoned. In this view, dark energy is a property of space itself. Empty space, rather than being truly empty, has an inherent energy density that doesn't dilute as the universe expands. As space grows, more dark energy appears, pushing the expansion to accelerate. Einstein originally introduced the cosmological constant to balance gravity and keep the universe static, neither expanding nor contracting. When Edwin Hubble discovered that the universe was indeed expanding, Einstein reportedly called the cosmological constant his greatest blunder. But now it seems he may have been right all along, though for reasons he never imagined. Another possibility is that dark energy isn't constant at all, but rather a dynamic field that changes over time, sometimes called quintessence after the classical fifth element. In this scenario, dark energy could strengthen or weaken, potentially even changing the fate of the universe. If dark energy weakens, the expansion might slow down again. If it strengthens, the universe could expand so rapidly that even atoms themselves are torn apart in what cosmologists cheerfully call the Big Rip. There are more exotic possibilities still. Perhaps our understanding of gravity itself is incomplete, and what we interpret as dark energy is actually a sign that Einstein's general relativity breaks down on cosmic scales. Maybe there are extra dimensions beyond the three of space and one of time that we experience, and gravity leaks into these dimensions, appearing weaker on large scales and creating the illusion of accelerating expansion. Or perhaps the answer lies in the quantum realm. When physicists try to calculate the energy of empty space using quantum mechanics, they get a number that's not just wrong, but spectacularly wrong, larger than the observed value of dark energy by a factor of 10 to the 120th power. That's like predicting someone's height and being off by more than the size of the observable universe. It's such a dramatically bad prediction that it suggests we're missing something fundamental about how quantum mechanics and gravity work together. The mystery deepens when we consider dark energy's behavior over time. Unlike matter, which dilutes as the universe expands, dark energy maintains a constant density. If you have a cubic meter of space containing a certain amount of dark energy, and the universe expands so that cubic meter becomes 8 cubic meters, you now have 8 times as much dark energy. It's as if the universe has an inexhaustible source of this mysterious component, constantly creating more of itself as space grows. This has profound implications for the future. As the universe continues to expand and accelerate, galaxies that are not gravitationally bound to our local group will gradually disappear from view. Their light will be stretched to longer and longer wavelengths until it fades beyond detection. Billions of years from now, an astronomer in the Milky Way might look out at the night sky and see only our local cluster of galaxies, with empty darkness beyond. They might conclude that the universe is small, static, and largely empty, never knowing about the vast cosmic web of galaxies that we can see today. Eventually, if dark energy continues to dominate, the universe will become a cold, dark, and lonely place. Stars will burn out, black holes will evaporate through Hawking radiation, and even protons might decay, leaving behind only a thin soup of elementary particles separated by ever-increasing distances. It's a fate that cosmologists call heat death, though it's really more of a cold death, the universe expanding and cooling until nothing interesting can happen anymore. But that's trillions upon trillions of years in the future, so unimaginably distant that our sun will have lived and died and been forgotten countless times over. For now, dark energy is our invisible companion, gently pushing the cosmos apart at just the right rate to create the universe we see around us. If dark energy were much stronger, galaxies never would have formed. If it were much weaker, the universe might have collapsed back in on itself long ago. The search for answers continues. Ambitious surveys like the Dark Energy Survey and the upcoming Vera Rubin Observatory are mapping millions of galaxies, looking for subtle patterns in their distribution that might reveal dark energy's secrets. Space missions are being planned to study supernovae and other cosmic distance markers with unprecedented precision. Deep underground, physicists are conducting experiments to search for exotic particles that might constitute dark energy. And yet, for all our sophisticated instruments and elegant theories, dark energy remains as mysterious as ever. It's a reminder that the universe still holds secrets, still has the power to surprise us, still whispers in languages we're only beginning to learn. We live in a cosmos dominated by forces we don't understand, shaped by substances we can't see, following rules we haven't discovered. In a strange way, this ignorance is comforting. It means there are still mountains to climb, still questions to ask, still wonders waiting to be uncovered. Dark energy ensures that the universe will continue expanding, continue evolving, continue surprising us for as long as there are minds to contemplate it. And perhaps that's the most beautiful thing about dark energy. It guarantees that the cosmic story is far from over. The universe is not winding down or settling into boring equilibrium. It's accelerating into an unknown future, carrying us along on a journey whose destination we cannot foresee. We are passengers on a ship sailing into uncharted waters, and the wind filling our sails is made of something we've never seen. So tonight, as you drift towards sleep, remember that you're part of this grand adventure. Every atom in your body is riding the wave of cosmic expansion, gently carried along by the mysterious force that shapes space itself. You're not separate from the universe's greatest mystery. You're embedded within it, a conscious observer made of stardust, contemplating the invisible energy that will determine the fate of everything. The universe is expanding around you, through you, carrying you forward into tomorrow and beyond. And somewhere in that vast darkness, dark energy continues its patient work, writing the future of the cosmos in a script we're still learning to read. Sweet dreams, fellow traveler. The universe has many more secrets to share. The universe is vast beyond human comprehension, filled with billions of galaxies, each containing billions of stars. Yet despite all our technological advances and deep space observations, there remains something profoundly mysterious about the very fabric of reality itself. We know that ordinary matter, the stuff that makes up planets, stars, and everything we can see and touch, accounts for less than 5% of the total energy in the universe. The remaining 95% consists of two invisible components that we can detect only through their gravitational effects: dark matter and dark energy. While dark matter at least clumps together and helps form the cosmic web that shapes galaxy formation, dark energy is far stranger, a force that appears to be pushing the universe apart at an ever-accelerating rate. This accelerating expansion was one of the most shocking discoveries in modern cosmology. For decades after Edwin Hubble first showed us that the universe was expanding, scientists assumed that gravity would eventually slow this expansion down. The mutual gravitational attraction of all matter in the universe should act like a cosmic brake, gradually reducing the expansion rate until perhaps the universe might even collapse back in on itself in a reverse Big Bang scenario. But in the 1990s, two independent teams of astronomers studying distant supernovae made a discovery that turned this assumption upside down. Instead of slowing down, the expansion of the universe was speeding up. The implications were staggering. Something was counteracting gravity on the largest scales, pushing galaxies away from each other with increasing vigor. This mysterious force was dubbed dark energy, and it appears to make up roughly 68% of the total energy content of the universe. Unlike dark matter, which at least behaves somewhat predictably by clumping together under its own gravity, dark energy seems to be spread uniformly throughout space, maintaining a constant density even as the universe expands. This means that as space grows larger, the total amount of dark energy increases proportionally, providing an ever stronger push against gravitational attraction. But what exactly is dark energy? The honest answer is that we don't really know. It's one of the deepest mysteries in physics, a placeholder name for our ignorance about 70% of everything that exists. The leading candidate is something called the cosmological constant, a concept that Einstein first introduced and later called his greatest blunder. Einstein had originally added this constant to his equations to allow for a static universe, but when Hubble discovered cosmic expansion, Einstein abandoned the idea. Now it seems he may have been onto something after all, though for entirely different reasons than he originally imagined. The cosmological constant represents the energy of empty space itself, a baseline level of energy that exists even in a perfect vacuum. Quantum mechanics tells us that even empty space is not truly empty, but filled with virtual particles constantly popping in and out of existence. This quantum foam should contribute to the energy of space, and if this energy has the right properties, it could drive cosmic acceleration. However, when physicists try to calculate how much vacuum energy there should be based on quantum field theory, they get an answer that's off by a factor of 10 to the power of 120. This is arguably the worst prediction in the history of science, suggesting that our understanding of either quantum mechanics or gravity or both is fundamentally incomplete. Alternative explanations for dark energy include the possibility that it's not a constant at all, but rather a dynamic field that changes over time and space. Just as electromagnetic fields can vary in strength and direction, perhaps dark energy is carried by a field that evolves as the universe ages. Some theories propose that this field, often called quintessence after the mythical fifth element, might have different properties in different regions of space, or might interact weakly with ordinary matter in ways we haven't yet detected. If dark energy is indeed a field, it might eventually decay or change its behavior, potentially altering the future evolution of the universe in ways we can't currently predict. Another possibility is that dark energy isn't a thing at all, but rather a sign that our understanding of gravity itself is incomplete. Einstein's general relativity has passed every test we've thrown at it on scales from laboratory experiments to the solar system, but perhaps it breaks down on the vast scales of cosmic expansion. Modified theories of gravity attempt to explain cosmic acceleration without invoking mysterious dark energy, suggesting instead that gravity behaves differently over enormous distances or in regions of extremely low density. These theories face their own challenges in matching all the observational data, but they remind us that extraordinary claims require extraordinary evidence, and the existence of dark energy is certainly an extraordinary claim. The consequences of dark energy for the future of the universe are both fascinating and somewhat melancholy. If dark energy continues to dominate cosmic evolution as it does today, the universe will keep expanding at an accelerating rate. Over time, galaxies not gravitationally bound to our local group will recede beyond our observable horizon, disappearing from view as their light becomes too red-shifted to detect. The cosmic web that currently connects galaxies across vast distances will stretch and thin until only isolated galaxy clusters remain, like islands in an ever-expanding ocean of space. Even these island clusters won't last forever. As dark energy continues its relentless push, it will eventually overcome even the gravitational bonds holding galaxy clusters together, then individual galaxies, then solar systems, and ultimately even atoms themselves. This scenario, known as the Big Rip, would occur in the far distant future if dark energy continues to strengthen over time. More likely, if dark energy remains constant, the universe will simply continue expanding and cooling until all the stars burn out, leaving behind a cold, dark cosmos populated only by black holes, slowly evaporating through Hawking radiation over timescales that dwarf the current age of the universe. But these cosmic endings are still trillions of years in the future, and our understanding of dark energy remains so limited that dramatic surprises are certainly possible. Perhaps dark energy will weaken or change sign, leading to cosmic collapse. Perhaps it will reveal connections to other mysteries in physics, helping us understand the relationship between quantum mechanics and gravity. Or perhaps the solution will be even stranger than anything we've yet imagined, requiring us to fundamentally revise our concepts of space, time, and energy. The search for answers continues through multiple approaches. Ground-based and space-based telescopes survey millions of galaxies to map the expansion history of the universe with ever greater precision. Experiments deep underground search for potential interactions between dark energy and ordinary matter. Theoretical physicists explore new mathematical frameworks that might accommodate both quantum mechanics and gravity while explaining cosmic acceleration. Each new observation constrains the possibilities slightly, gradually narrowing the range of viable theories. What makes dark energy particularly puzzling is not just its mysterious nature, but also its apparent fine-tuning. The observed value of dark energy density is remarkably small by fundamental physics standards, yet it's also precisely the right magnitude to become important at roughly the current epoch in cosmic history. If dark energy were much stronger, it would have prevented galaxies from forming in the first place. If it were much weaker, we wouldn't have detected its effects yet. This cosmic coincidence problem suggests either that we're living at a special time in cosmic history, or that there's something deeper we don't understand about the connection between dark energy and the other components of the universe. Some physicists have proposed anthropic explanations, suggesting that we observe this particular value of dark energy simply because it's compatible with the existence of observers like ourselves. In a multiverse scenario, with different regions having different dark energy densities, only those regions with suitable values would develop the complex structures necessary for life. While this anthropic reasoning is controversial and difficult to test, it highlights how the mystery of dark energy connects to fundamental questions about the nature of existence itself. The experimental search for dark energy has led to increasingly sophisticated surveys and instruments. Projects like the Dark Energy Survey, the Euclid Space Mission, and the upcoming Vera Rubin Observatory are mapping the positions and properties of billions of galaxies to trace how cosmic expansion has evolved over time. By studying how the clustering of galaxies has changed as the universe has aged, astronomers hope to distinguish between different models of dark energy and perhaps detect subtle variations in its properties across space and time. Meanwhile, laboratory experiments search for signs that dark energy might interact with ordinary matter through previously unknown forces. If dark energy is carried by a field that couples weakly to normal matter, it might be detectable through precision measurements of fundamental constants, tests of the equivalence principle, or searches for new long-range forces. So far, these experiments have found no clear signals, but they continue to push the boundaries of sensitivity and explore new parameter ranges. Theoretical work on dark energy has expanded our understanding of possible mechanisms and their observational consequences. String theory, loop quantum gravity, and other approaches to quantum gravity suggest new ways that the energy of space itself might arise and evolve. Some models connect dark energy to the physics of extra dimensions, while others link it to phase transitions in exotic quantum fields. Each theoretical framework makes different predictions for how dark energy should behave over time, and how it might be detected through astronomical observations or laboratory experiments. The mystery of dark energy also highlights the interconnected nature of fundamental physics. Understanding why the vacuum has the energy density it does requires grappling with the deepest questions about quantum field theory, general relativity, and the nature of space-time itself. The solution might require new physics beyond the standard model of particle physics, or it might emerge from a better understanding of how quantum mechanics and gravity fit together into a unified theory. As we drift towards sleep tonight, pondering the vast mystery of dark energy, we're confronted with the humbling reality that the universe is far stranger and more complex than our everyday experience suggests. The very space between the stars, seemingly empty and passive, may be filled with an invisible energy that shapes the destiny of everything that exists. This energy, whatever it is, reminds us that our knowledge remains incomplete and that the cosmos still holds secrets waiting to be discovered. The story of dark energy is still being written, each new observation and theoretical insight adding another piece to an enormous puzzle. Whether the solution will come from revolutionary new physics or from a deeper understanding of concepts we already know remains to be seen. What's certain is that the universe continues to surprise us, challenging our assumptions and expanding our sense of wonder about the reality we inhabit. In the quiet darkness of your room tonight, as you settle into sleep, remember that you exist within a universe dominated by forces we don't yet understand, pushed apart by an energy we can't see or touch, but whose effects shape everything around us. It's a reminder of how much mystery still surrounds us, how much beauty lies hidden in the unknown, and how the greatest discoveries may still lie ahead, waiting for future generations of scientists to uncover the secrets of dark energy and the accelerating cosmos. Welcome back to our journey through the expanding cosmos, where mysteries unfold like distant galaxies, and the universe keeps secrets written in the language of light and gravity. We've traveled far together, from the first moments after the Big Bang to the birth of stars, from the cosmic dark ages to the formation of the first galactic cities. We've seen how gravity sculpts matter, how dark energy stretches space, and how time itself becomes a canvas on which the universe paints its story. But now we arrive at perhaps the most puzzling chapter of all. As we peer deeper into the cosmos, as our telescopes grow more powerful and our understanding more refined, we've discovered something extraordinary and deeply unsettling. The universe isn't just expanding, it's accelerating its expansion, driven by a force so mysterious that we've had to give it a name that admits our ignorance: dark energy. This invisible puppeteer, this cosmic conductor, orchestrating the grandest symphony of all, makes up about 68% of everything that exists. It's not matter as we know it, not radiation, not even the elusive dark matter that holds galaxies together. It's something else entirely, something that pushes rather than pulls, something that grows stronger as space itself grows larger. Imagine, if you will, blowing up a balloon. Normally, as the balloon stretches, it becomes harder to inflate further. The rubber resists, the pressure builds, and eventually you reach a limit. But the universe is like a balloon that becomes easier to inflate the bigger it gets. The more space there is, the more dark energy fills it, and the faster everything flies apart. It's as if the very fabric of reality has developed an appetite for emptiness, a preference for solitude on the grandest possible scale. We discovered this cosmic peculiarity quite by accident, as many of the universe's most profound secrets are revealed. In the late 1990s, two teams of astronomers were studying distant supernovas, those spectacular stellar explosions that briefly outshine entire galaxies. They were using these cosmic lighthouses as standard candles, measuring how bright they appeared from Earth to determine how far away they were and how fast they were receding from us. What they found defied every expectation. The distant supernovas were fainter than they should have been, which meant they were farther away than anticipated. This could only mean one thing: the expansion of the universe was not slowing down under the influence of gravity, as everyone had assumed. Instead, it was speeding up. Something was pushing the cosmos apart with ever-increasing vigor. The discovery sent ripples through the scientific community like a pebble dropped into a still pond. Einstein's equations, which had served as our roadmap to the cosmos for nearly a century, suddenly needed a new term, a cosmological constant that he had once called his greatest blunder. But now it seemed that constant, that mathematical placeholder for something we didn't understand, might actually describe something real and profoundly important. Dark energy is everywhere and everywhen. It fills the emptiest voids between galaxies. It permeates the space between atoms, and it's been growing in influence since the universe was young. In the early cosmos, when matter and radiation were dense and tightly packed, gravity dominated the cosmic dance. But as the universe expanded and matter spread thin, dark energy began to assert itself, like a quiet voice that grows stronger as the crowd falls silent. Think of it this way. If you have a box and you fill it with marbles, the marbles represent matter. As you make the box bigger, the marbles spread out, becoming less dense. But dark energy is different. It's as if every cubic inch of empty space in that box contains the same amount of invisible energy. So as the box grows, the total dark energy grows too. Eventually, there's so much empty space that dark energy overwhelms everything else. This leads us to a profound realization about the future of our universe. If dark energy continues to dominate, and current observations suggest it will, then the cosmos is headed for a fate both beautiful and melancholy. Galaxies will drift apart, slowly at first, then faster and faster, until they disappear beyond each other's horizons like ships sailing past the edge of a spherical sea. Billions of years from now, an astronomer in some distant galaxy will look up at the night sky and see only darkness punctuated by the stars of their own galactic home. The cosmic microwave background, that ancient afterglow of the Big Bang that currently whispers to us from every direction, will be stretched and cooled until it fades into imperceptible silence. The universe will appear to be nothing more than a single island of light surrounded by infinite emptiness. But even that won't be the end. Stars will continue to be born for trillions of years, but eventually the gas will run out, the stellar nurseries will close, and one by one the lights will go out. First, the massive blue giants will exhaust their fuel and collapse into black holes or explode as supernovas. Then the sun-like stars will swell into red giants before fading to white dwarfs. Finally, even the smallest red dwarfs, those miserly stellar embers that burn for hundreds of billions of years, will flicker and die. In this far future, the universe will be a cold, dark place, populated only by stellar remnants, white dwarfs, neutron stars, and black holes drifting through the void like cosmic fossils. Even these will not last forever. White dwarfs will slowly cool and fade, neutron stars will spin down, and through the mysterious process of Hawking radiation, even black holes will eventually evaporate, larger ones taking longer than smaller ones, but all of them destined to disappear into the quantum foam. This ultimate fate, sometimes called the heat death of the universe, won't arrive for an unimaginably long time. We're talking about timescales that make the current age of the universe seem like a brief moment. By the time the last black hole evaporates, more time will have passed than there are atoms in the observable universe today. It's a number so large that it becomes almost meaningless, a duration that stretches beyond our ability to comprehend. Yet there's something oddly comforting about this cosmic timeline. It means that life, intelligence, and beauty have eons upon eons to flourish. Civilizations could rise and fall millions of times over. New forms of existence we can't even imagine might emerge. The universe may be heading toward darkness, but it's in no hurry to get there. And who knows? Perhaps our understanding of dark energy is incomplete. Perhaps there are cycles we haven't discovered, mechanisms we haven't imagined, possibilities we haven't dreamed of. The universe has surprised us before with its complexity, its resilience, its capacity for reinvention. Maybe it has a few more tricks up its cosmic sleeve. For now, dark energy remains one of the great mysteries, a reminder that for all our telescopes and equations, for all our careful observations and elegant theories, the universe still holds secrets. It's a vast, expanding stage on which the drama of existence plays out, driven by forces we're only beginning to understand. So as we drift through this moment in cosmic history, suspended between the fire of the Big Bang and the cold of the far future, we find ourselves witnesses to something extraordinary. We exist in an era when galaxies still shine, when stars still burn, when the night sky is rich with light and possibility. We are here to wonder, to question, to reach out with our instruments and our imagination toward the edges of understanding. The universe may be accelerating away from itself, but for now, for this brief and precious epoch, we are here to marvel at its beauty, to puzzle over its mysteries, and to tell its story. Dark energy may be pulling the cosmos apart, but it has also given us the gift of time, billions upon billions of years to explore, to dream, and to discover what it means to be conscious creatures in an ever-expanding sea of stars. Sleep well, fellow travelers, knowing that even as the universe stretches toward its distant destiny, you are part of something magnificent and mysterious, something that continues to unfold in ways both beautiful and strange. Hello there, and welcome to The Sleepy Scientist, where curiosity meets calm and science gently drifts you toward dreams. Tonight, we're embarking on one of the most mind-bending journeys our cosmos has to offer. We're going to explore dark energy, the mysterious force that's not just expanding our universe, but accelerating that expansion in ways that challenge everything we thought we knew about reality itself. Before we begin drifting through this cosmic mystery, I'd love to know where in the world you're listening from tonight and what time it is in your corner of the universe. Drop a comment below. There's something wonderfully grounding about knowing we're all floating together on this pale blue dot, scattered across time zones, yet united by our shared curiosity about the vast unknown. And if you find tonight's gentle journey through the cosmos soothing or intriguing, I'd be ever so grateful if you gave this video a like and perhaps subscribed. It helps other sleepy minds find their way to this quiet corner of scientific wonder. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does well, at least you'll drift off knowing a bit more about the universe's deepest secret. So settle in, breathe slowly, let your thoughts soften, because tonight we're going to explore something truly extraordinary, the invisible force that's writing the future of everything that ever was or ever will be. Imagine for a moment that you're watching a movie and suddenly the screen starts stretching, not just getting bigger, but the space between every pixel expanding, the characters moving apart, the scenery growing more distant. This isn't a malfunction, it's exactly what's happening to our universe right now. At this very moment, space itself is expanding, and not just expanding, but doing so at an ever-increasing rate. This acceleration, this cosmic stretching, is driven by something we call dark energy. And despite its rather ominous name, it's not dark in the way shadows are dark. It's dark in the way that mysteries are dark. Invisible, undetectable, yet undeniably there, shaping the very fabric of reality in ways we're only beginning to understand. Dark energy makes up roughly 70% of everything that exists in our universe. Think about that for a moment. Nearly 3/4 of all existence is composed of something we can't see, can't touch, can't directly measure, and barely comprehend. It's as if you discovered that most of your house was made of invisible rooms you never knew existed. To understand why this is so remarkable, we need to step back and consider what we thought we knew about the universe's expansion for most of the 20th century. After Edwin Hubble discovered that galaxies were moving away from us, scientists assumed this expansion was slowing down after all. If you throw a ball into the air, gravity pulls it back down. It doesn't suddenly start accelerating upward. The universe seemed to follow similar logic. The Big Bang had given everything an initial outward push, but the gravitational attraction between all matter should have been gradually slowing that expansion, like cosmic brakes, gently applied across billions of years. We expected the universe to either eventually stop expanding and collapse back in on itself, or continue expanding, but at an ever-decreasing rate. Then in the late 1990s, two teams of astronomers made a discovery that changed everything they were studying. Distant supernovae, incredibly bright stellar explosions that can be seen across vast cosmic distances. These particular supernovae, called type 1a supernovae, are wonderfully useful because they all explode with roughly the same brightness, making them excellent cosmic candles for measuring distances. What these teams found was shocking. The distant supernovae were dimmer than expected, which meant they were farther away than they should have been if the universe's expansion were slowing down. Instead of cosmic brakes being applied, it was as if someone had pressed the accelerator. The universe's expansion wasn't just continuing, it was speeding up. This discovery earned the 2011 Nobel Prize in Physics and fundamentally changed our understanding of the cosmos. We suddenly realized that some unknown force was overpowering gravity on the largest scales, pushing space itself apart with ever-increasing vigor. They called this mysterious force dark energy. But what exactly is dark energy? The honest answer is we don't really know. It's one of the most profound mysteries in modern science, like trying to understand music by studying silence or comprehending light by examining darkness. We know dark energy is there because we can see its effects, but the thing itself remains stubbornly hidden. Think of it this way. Imagine you're in a room and you notice that all the furniture is slowly moving away from you, getting farther and farther apart. And not only that, but the rate at which they're separating is increasing. You can't see what's pushing them, you can't feel it, you can't measure it directly, but something is clearly at work. That's essentially our situation with dark energy. One of the leading theories suggests that dark energy might be related to the cosmological constant, a concept Einstein introduced in his equations of general relativity. Einstein originally added this constant to allow for a static universe, one that neither expanded nor contracted. But when Hubble discovered cosmic expansion, Einstein called the cosmological constant his greatest blunder. Ironically, what Einstein considered his biggest mistake might actually be his greatest insight. The cosmological constant represents the energy density of empty space itself, suggesting that even the vacuum of space has energy, and this vacuum energy, if it exists, could be driving the accelerated expansion. But here's where things get truly puzzling when physicists try to calculate what this vacuum energy should be based on quantum mechanics. They get an answer that's off by a factor of about 10 to the power of 120. That's not a small error. That's the difference between the size of an atom and the size of the observable universe. It's arguably the worst prediction in the history of physics. Another possibility is that dark energy isn't constant at all, but instead involves what's called quintessence, a dynamic field that changes over time, named after the fifth element in ancient philosophy. Quintessence would be a kind of energy field permeating all of space, slowly evolving and driving cosmic acceleration. Some scientists propose even more exotic explanations. Perhaps our understanding of gravity itself is incomplete. Maybe Einstein's general relativity, while incredibly successful, needs modification on cosmic scales. These modified gravity theories suggest that what we attribute to dark energy might actually be a sign that gravity behaves differently over vast distances than we expect. There are theories involving extra dimensions, parallel universes, and quantum effects that we haven't yet discovered, each attempting to explain why the universe seems determined to tear itself apart with ever-increasing enthusiasm. It's a bit like being detectives at a crime scene, where the only evidence is that something extraordinary happened, but all the usual suspects have solid alibis. What makes dark energy even more mysterious is how perfectly balanced it seems to be. If dark energy were much stronger, the universe would have expanded so rapidly that galaxies, stars, and planets could never have formed. If it were much weaker, gravity would have won, and the universe might have collapsed long ago. Instead, we find ourselves in a cosmic Goldilocks zone, where dark energy is just right to allow for the complex structures we see today, including us. This fine-tuning raises profound questions. Is there something special about our universe, or are we simply lucky enough to exist in the one possible universe out of countless others, where the conditions happen to be just right for complexity and life to emerge? It's a question that touches not just physics, but philosophy and our very understanding of our place in the cosmos. The effects of dark energy aren't just academic, they're actively shaping the future of everything we can see in the night sky. As space continues to expand at an accelerating rate, galaxies that aren't gravitationally bound to our local group will eventually recede beyond our cosmic horizon, their light stretched to wavelengths we can no longer detect. Billions of years from now, future astronomers in our galaxy might look up at a night sky that appears almost empty, unable to see the rich tapestry of distant galaxies that we observe today. They might conclude that our galaxy is alone in the universe, unaware of the vast cosmic community that once sparkled in their predecessors' telescopes. On even longer timescales, trillions of years in the future, dark energy might drive what cosmologists call the heat death of the universe, as expansion accelerates and matter becomes ever more dilute. The universe could become a cold, dark, and lonely place where the last stars have burned out and black holes themselves have evaporated, leaving nothing but elementary particles drifting through an ever-expanding void. But these are timescales so vast, they're almost meaningless in human terms. Trillions of years from now, our sun will have long since exhausted its fuel. Our galaxy will have merged with Andromeda, and the very atoms in our bodies will have been recycled countless times through stellar furnaces and planetary systems yet to be born. For now, in our cosmic moment, dark energy continues its patient work, stretching space, pushing galaxies apart, and writing the future of the universe in a language we're still learning to read. Every second that passes, space itself grows a little larger. The distances between galaxy clusters increase imperceptibly, and the mysterious force that drives this expansion remains as enigmatic as ever. What's truly remarkable is that we've detected this at all, that human beings, with our brief lifespans and limited perspective, have managed to discern that something invisible and incomprehensible is reshaping the cosmos on scales beyond imagination. It speaks to the power of scientific inquiry, the ability to ask questions of the universe and occasionally receive answers, even if they're answers that lead to even deeper mysteries. As you lie there tonight, perhaps looking up at the stars, if you're fortunate enough to see them, remember that the space between you and those distant suns is gently expanding. The photons, traveling from those stars to your eyes, have journeyed through a universe that's been stretching the entire time they've been in flight. And somewhere in the quantum foam of space-time itself, dark energy continues its silent work. We may not understand what dark energy is, we may not know why it exists or how it operates, but we can marvel at the fact that the universe still holds such profound secrets, that there are forces at work beyond our current comprehension, shaping reality in ways we're only beginning to glimpse. In a strange way, dark energy reminds us of how much we don't know about the cosmos we inhabit. It's a humbling reminder that for all our scientific advances, our sophisticated instruments, and our elegant theories, the universe remains largely mysterious, still capable of surprising us with revelations that overturn our most basic assumptions about how things work. Perhaps that's one of the most beautiful aspects of dark energy, not just what it might be, but what it represents, the enduring mystery of existence. The fact that the universe we call home is still writing its story, and we're privileged to be here during one of the chapters where conscious beings can contemplate the nature of their cosmic environment. So as you drift towards sleep tonight, carried along by the expanding space-time that dark energy sculpts, know that you're part of something magnificent and mysterious. A universe that's simultaneously comprehensible enough for us to study and mysterious enough to keep surprising us, a cosmos where invisible forces shape visible reality and where the deepest questions often lead to the most profound sense of wonder. The universe is expanding, it's accelerating, and it's carrying all of us along for the ride through the vast, mysterious dance of dark energy. Sweet dreams, fellow cosmic travelers, wherever this expanding universe may take us next. Welcome back to The Sleepy Scientist, where cosmic curiosities drift gently toward dreams and the universe whispers its secrets in the softest voice. Tonight, we're floating through one of the most profound mysteries of our time, a force so vast and invisible that it makes up nearly 70% of everything that exists, yet we can barely grasp what it is. We're exploring dark energy, the enigmatic force that's not just expanding our universe, but accelerating that expansion in ways that challenge everything we thought we knew about reality. If you're settling in for the night, perhaps curled up somewhere comfortable with the weight of the day finally lifting from your shoulders, you've found the perfect companion for this gentle journey into the cosmic unknown. And if you're finding these sleepy explorations of science soothing, I'd be ever so grateful if you'd give this video a gentle like or subscribe to join our quiet community of curious minds scattered across the globe. Now, before we dive deeper into this mystery that's literally stretching the fabric of space itself, let me ask you this. Where in the world are you listening from tonight? And what time is it in your corner of the universe? There's something beautifully fitting about contemplating the expansion of space while we're all connected across different time zones, each of us experiencing this moment in our own unique slice of cosmic time. So let's continue our journey through the expanding cosmos, where dark energy reigns supreme, quietly but relentlessly, pushing the very boundaries of existence further and further apart. The story of dark energy begins not with what we can see, but with what we expected to see and didn't. Picture the universe as a vast cosmic theater where gravity has always been the star of the show. For most of human history, we understood gravity as the great gatherer, the force that pulls things together, holds planets in their orbits, and keeps galaxies from drifting apart like scattered leaves in an autumn wind. When Einstein gave us his theory of general relativity in the early 20th century, it painted a picture of a universe where massive objects bend the fabric of space-time itself, creating the curves and valleys that we experience as gravitational attraction. It was elegant, it was beautiful, and it suggested something profound about the fate of our cosmos, that after the initial expansion from the Big Bang, gravity should eventually slow everything down. The prevailing wisdom was straightforward and comforting in its logic. Yes, the universe was expanding, stretching outward from that primordial moment of creation. But surely this expansion must be decelerating. After all, every galaxy, every star, every particle of matter was pulling on every other through the persistent tug of gravity. It was like throwing a ball into the air. No matter how hard you throw it, gravity will eventually slow it down, stop it, and pull it back. Scientists even had names for the possible futures this suggested. Perhaps the universe would expand forever, but more and more slowly, growing cold and dark in what they called the heat death scenario. Or maybe, just maybe, there was enough matter and gravitational pull to eventually halt the expansion entirely, causing everything to collapse back in on itself in a reverse Big Bang they poetically named the Big Crunch. Both scenarios made sense. Both fit our understanding of how gravity works. Both seemed to honor the fundamental forces we'd spent centuries learning to understand and predict. The universe, in this view, was like a vast cosmic pendulum, either swinging outward forever with decreasing energy or eventually swinging back toward its starting point. But the universe, as it so often does, had other plans entirely. In the late 1990s, two teams of astronomers set out to measure exactly how much this cosmic deceleration was occurring. They weren't looking to revolutionize physics or discover something that would fundamentally challenge our understanding of reality. They simply wanted to measure how fast the expansion of the universe was slowing down. It seemed like a straightforward enough question, the kind of precision measurement that would help us understand which of those cosmic futures awaited us. These teams, led by researchers like Saul Perlmutter, Brian Schmidt, and Adam Rees, used some of the most distant and brilliant objects in the universe as their cosmic measuring sticks, type Ia supernovae. These stellar explosions are remarkably consistent in their brightness, earning them the nickname standard candles. When a white dwarf star accumulates matter from a companion star and reaches a critical mass, it explodes in a supernova with a predictable luminosity. By comparing how bright these explosions appear to us with how bright we know they actually are, astronomers can calculate their distance with remarkable precision. The plan was elegant in its simplicity. Measure the distance to these supernovae, measure how fast they're moving away from us using the redshift of their light, and plot the relationship between distance and recession velocity. If the universe's expansion was slowing down as expected, distant supernovae should be closer than they would be in a universe expanding at a constant rate. The data would reveal the deceleration, confirming our understanding of cosmic evolution, but when the results came in, they told a completely different story. The distant supernovae weren't closer than expected. They were farther away. Much farther away. The universe wasn't slowing down at all. Instead, it was speeding up, expanding faster and faster with each passing eon. The discovery was so unexpected, so contrary to everything physics predicted, that both teams initially thought they'd made an error. They checked their calculations, recalibrated their instruments, questioned their assumptions, and ran the analysis again and again. But the result remained the same. The expansion of the universe is accelerating. This revelation didn't just challenge our understanding of cosmic evolution, it shattered it entirely. If gravity was the only significant force acting on cosmic scales, the expansion should be slowing down, not speeding up. Something else had to be at work, something powerful enough to overcome the gravitational attraction of all the matter in the universe, something that could push space itself apart with ever-increasing vigor. Scientists gave this mysterious force a name that perfectly captured both its importance and our ignorance about it: dark energy. Not dark because it's sinister or hidden in shadow, but dark because it doesn't interact with light at all. We can't see it, we can't touch it, we can't measure it directly. We know it exists only through its effects, through the way it stretches the very fabric of space and drives galaxies apart at an accelerating pace. The implications were staggering. If dark energy makes up about 68% of the total energy density of the universe, then everything we can see and touch and study, all the stars, galaxies, planets, and even all the dark matter we discovered earlier, represents less than a third of what actually exists. We are living in a universe dominated by something we don't understand, something that defies our most fundamental theories about how reality should work. And perhaps most humbling of all, this discovery came not from theoretical predictions or elegant mathematical frameworks, but from the simple act of looking at exploding stars and carefully measuring their light. Sometimes the universe's greatest secrets are hiding in plain sight, waiting for us to look closely enough to notice that our expectations don't match reality. The discovery of dark energy was like opening what you thought was a familiar book, only to find that most of the pages were written in an unknown language, challenging everything you believed you understood about the story being told. Now, when faced with such a profound mystery, the scientific mind naturally begins to theorize, to propose explanations that might account for this strange, accelerating expansion. Over the decades since dark energy's discovery, researchers have put forward several compelling possibilities, each offering a different perspective on what this invisible force might actually be. The first and perhaps most straightforward explanation is that dark energy is simply a property of space itself. This idea harks back to Einstein, who once introduced something called the cosmological constant into his equations of general relativity. Originally, Einstein added this constant as a kind of anti-gravitational force to balance gravity and keep the universe static, which was the prevailing belief at the time. When Edwin Hubble later discovered that the universe was expanding, Einstein famously called the cosmological constant his greatest blunder and removed it from his equations. But perhaps Einstein's so-called blunder was actually one of his most prescient insights. In this modern interpretation, the cosmological constant represents a fundamental energy density of empty space itself. Even in the most perfect vacuum, completely devoid of matter and radiation, space might still possess an inherent energy that creates a kind of gravitational repulsion. This vacuum energy would remain constant throughout space and time, providing a steady pressure that drives cosmic acceleration. The beauty of this explanation is its simplicity and elegance. Dark energy wouldn't be some exotic new force or mysterious substance. It would be an intrinsic property of the universe itself, woven into the very fabric of space-time. As the universe expands and creates more space, it also creates more dark energy, maintaining a constant density that continues to accelerate expansion indefinitely. However, when physicists try to calculate what this vacuum energy should be based on quantum mechanics, they run into what might be the most embarrassing discrepancy in the history of science. The theoretical predictions exceed the observed value of dark energy by a factor of about 10 to the power of 120. That's not a small error. It's a number so large, it makes the age of the universe in seconds look tiny by comparison. This enormous disagreement between theory and observation suggests that either our understanding of quantum mechanics is fundamentally flawed, or the cosmological constant explanation is missing something crucial. A second possibility is that dark energy is not constant but dynamic, changing over time and space. Scientists call this hypothetical substance quintessence, named after the classical fifth element that ancient philosophers believed filled the heavens. Unlike the cosmological constant, quintessence would be a field that evolves throughout cosmic history, perhaps growing stronger or weaker as the universe ages. This dynamic dark energy could be driven by a scalar field similar to the inflaton field thought to have caused the rapid expansion of the early universe during cosmic inflation. The field would have its own potential energy landscape, rolling down hills and valleys of energy like a ball rolling through a complex terrain. As it moves through this landscape, the field's energy density and pressure would change, altering the rate of cosmic acceleration. Quintessence offers more flexibility than the cosmological constant, potentially explaining not just the current accelerated expansion, but also variations in the expansion rate throughout cosmic history. Some models suggest that dark energy might have been negligible in the early universe, only becoming dominant as matter became more dilute through expansion. Others propose that dark energy might even change sign in the future, eventually reversing from accelerating expansion to accelerating contraction. The challenge with quintessence models is that they require careful fine-tuning to match observations. The field must evolve at just the right rate to produce the observed acceleration without conflicting with other cosmological data. While this flexibility is an advantage in some ways, it also makes quintessence harder to test and verify than the simpler cosmological constant. A third, more radical possibility is that dark energy doesn't exist at all, and our observations are telling us that our understanding of gravity itself needs to be modified. Perhaps Einstein's general relativity, for all its success in describing gravity on solar system scales, breaks down when applied to the vast distances and timescales of cosmology. Various modified gravity theories have been proposed to explain cosmic acceleration without invoking dark energy. Some suggest that gravity becomes repulsive at very large distances, naturally driving acceleration without requiring any mysterious new form of energy. Others propose that space itself has extra dimensions that become important on cosmic scales, altering the behavior of gravity in ways we don't experience locally. These modified gravity theories face the challenging task of reproducing all the successes of general relativity while also explaining cosmic acceleration. They must account for the precise orbital mechanics of planets, the bending of light around massive objects, the behavior of black holes, and countless other phenomena that general relativity describes with exquisite accuracy. while simultaneously explaining why the expansion of the universe is accelerating. Perhaps most intriguingly, some theories suggest that what we interpret as dark energy might actually be a sign that our universe is not isolated, but connected to a larger multiverse. In these scenarios, our cosmic acceleration could be driven by interactions with other universes or by the properties of the higher dimensional space in which our universe is embedded. Each of these explanations carries profound implications for our understanding of physics and our place in the cosmos. If dark energy is the cosmological constant, it suggests that empty space itself is alive with energy, constantly creating the force that drives cosmic evolution. If it's quintessence, it implies that the universe is filled with a dynamic field that has been shaping cosmic history since the beginning of time. If it requires modified gravity, it means our most successful theory of space-time needs fundamental revision. And if dark energy is somehow connected to extra dimensions or a multiverse, it opens the possibility that our entire observable universe is just a small part of a much grander and more complex reality. The truth is, we don't yet know which of these explanations is correct, or whether the real answer is something entirely different that hasn't been thought of yet. What we do know is that dark energy represents one of the deepest mysteries in modern science, a puzzle that challenges our understanding of space, time, matter, and energy at the most fundamental level. As we continue to gather data from increasingly sophisticated telescopes and experiments, we edge closer to understanding this cosmic enigma. But for now, dark energy remains beautifully mysterious, a reminder that the universe still holds secrets that can surprise and humble us, even after centuries of scientific discovery. Now, you might wonder how something so invisible and mysterious can have such concrete, measurable effects on the universe. The answer lies in understanding how dark energy interacts with the fabric of space itself, and how this interaction drives the accelerating expansion that astronomers observed in those distant supernovae. To understand dark energy's behavior, we need to think about energy density and pressure in ways that might seem counterintuitive at first. In our everyday experience, pressure usually pushes outward. When you inflate a balloon, the pressure inside pushes against the walls, expanding the balloon's volume. But dark energy operates with what physicists call negative pressure, and this negative pressure is the key to its remarkable ability to accelerate cosmic expansion. Imagine space itself as a kind of elastic medium that can be stretched and compressed. When something has positive pressure, like the air in a balloon, it resists being compressed and pushes outward when confined. But dark energy has negative pressure, which means it actually pulls inward on itself while simultaneously pushing space apart. This might sound contradictory, but it's this very contradiction that makes dark energy so effective at driving acceleration. Here's how it works. As the universe expands, it creates more space, and if dark energy has a constant density, then expanding space means creating more dark energy. Unlike matter, which becomes more dilute as space expands, dark energy maintains its density even as the universe grows larger. In fact, if dark energy is truly the cosmological constant, its density remains perfectly constant throughout all of space and time. This constant density is crucial because it means that as the universe expands and matter becomes more spread out and dilute, dark energy becomes increasingly dominant. In the early universe, when galaxies were closer together and matter was more concentrated, gravity was the stronger force and the expansion was indeed decelerating as expected. But as billions of years passed and the universe grew larger, matter became more dispersed while dark energy maintained its density. Think of it like a cosmic tug-of-war between gravity and dark energy. In the beginning, gravity had the advantage because matter was densely packed and its gravitational influence was strong. But as expansion diluted the matter, gravity's pull weakened while dark energy's push remained constant. Eventually, around 5 to 6 billion years ago, dark energy gained the upper hand, and the universe's expansion began to accelerate. What makes this even more remarkable is that dark energy doesn't just maintain the acceleration, it continuously increases it. Because dark energy density stays constant while matter density decreases, the ratio of dark energy to matter grows over time. This means that the acceleration itself is accelerating, with the expansion rate increasing at an ever faster pace. The mathematics of this process are encoded in what's called the equation of state for dark energy, which relates its pressure to its energy density. For the cosmological constant, this ratio is exactly -1, meaning the negative pressure is equal in magnitude to the energy density. This specific value is what produces the observed cosmic acceleration and ensures that dark energy density remains constant as space expands. But dark energy's effects extend beyond just driving expansion. It also influences the formation and evolution of cosmic structures like galaxies and galaxy clusters. While dark energy operates on the largest scales, pushing the overall fabric of space apart, it also affects how matter can clump together under gravity's influence. In regions where matter is already densely concentrated, like galaxy clusters, gravity can still overcome dark energy's influence and hold structures together. But dark energy makes it increasingly difficult for new large-scale structures to form as the universe ages. It's like trying to build sandcastles while someone slowly but steadily stretches the beach. Existing structures might hold together, but creating new ones becomes progressively more challenging. This has profound implications for the future evolution of cosmic structure. As dark energy continues to dominate, the universe will become increasingly smooth on large scales, with galaxy clusters becoming more isolated from each other. Eventually, regions of space that are not gravitationally bound will be stretched so far apart that light from one will no longer be able to reach the other. Dark energy also affects the geometry of space itself. The amount and properties of dark energy determine whether the universe is flat, curved inward like a sphere, or curved outward like a saddle. Current observations suggest that our universe is remarkably close to being perfectly flat, which places constraints on both the total amount of dark energy and its equation of state. Perhaps most intriguingly, dark energy creates what physicists call an event horizon in our future. Just as the event horizon around a black hole represents a boundary beyond which information cannot escape, the accelerating expansion driven by dark energy creates a boundary beyond which we will eventually lose contact with distant regions of the universe. Galaxies that are currently visible to us will eventually be carried away by expansion so rapidly that their light will never reach us again. This isn't because they're moving through space faster than light, that would violate relativity, but because space itself is expanding between us and them at an increasing rate. It's like trying to walk towards someone on a moving walkway that's speeding up faster than you can walk. You're not violating any speed limits, but you're still moving apart. The energy density of dark energy might seem small when measured in familiar units, about 6 protons worth of mass energy per cubic meter of space, but when multiplied by the vast volume of the observable universe, it represents an almost incomprehensible amount of energy. This energy is constantly doing work against gravity, pushing space apart and accelerating cosmic expansion. What's particularly mysterious is that this energy doesn't seem to dilute or dissipate as it does this work. In normal circumstances, when energy is used to do work, it gets converted into other forms or spread out and becomes less concentrated. But dark energy appears to maintain its density indefinitely, continuously creating more of itself as space expands. It's as if the universe has discovered a form of perpetual motion, constantly generating the energy needed to accelerate its own expansion. This behavior challenges some of our most fundamental assumptions about energy conservation and thermodynamics. While the universe as a whole still conserves energy in a technical sense, the way dark energy maintains its density while doing work seems to bend the rules in ways that would be impossible for any other form of energy we know. As we drift deeper into this cosmic mystery, we're left with the remarkable realization that the dominant component of our universe behaves in ways that seem almost magical, driving an acceleration that will ultimately determine the fate of everything we can see and touch and know. Dark energy is not just shaping the future of the cosmos, it's actively creating that future, moment by moment, as it stretches space itself toward destinations we can barely imagine. Hello there, and welcome to The Sleepy Scientist, your quiet corner of the cosmos, where curiosity meets calm and the mysteries of the universe gently rock you to sleep. Tonight, we're embarking on one final leg of our cosmic journey, exploring the enigmatic force that's pushing our universe apart faster and faster with each passing moment: dark energy. Before we drift into this celestial mystery, I'd love to know, where in the world are you listening from and what time is it in your corner of the night? Drop a comment below. I'm always amazed by how we gather from different time zones, united by wonder. And if you've enjoyed our journey through the expanding cosmos, consider giving this video a gentle like and perhaps subscribing so you don't miss our next stargazing session. Now, I do hope tonight's exploration isn't so fascinating that it keeps you awake, but if it does, well, at least you'll drift off knowing a bit more about the force that's reshaping the very fabric of reality. So settle in, let your shoulders drop. Breathe slowly. You're about to discover why the universe itself seems to be running away from us, and what that means for the ultimate fate of everything we see. The story begins not with dark energy itself, but with a surprise that shook the very foundations of cosmology. In the late 1990s, two teams of astronomers were racing to measure something that seemed straightforward: the rate at which the universe's expansion was slowing down. You see, everyone knew the universe was expanding. That had been established since Edwin Hubble's observations in the 1920s, but logic suggested that this expansion should be decelerating. After all, gravity pulls everything together. So surely the mutual gravitational attraction of all matter in the universe should be gradually slowing down this cosmic expansion, like a ball thrown upward, eventually succumbing to Earth's pull. The astronomers were using a particular type of exploding star, called a Type 1 A supernova, as their cosmic measuring stick. These stellar explosions are remarkably consistent in their brightness, making them perfect standard candles for measuring distances across the cosmos. By comparing how bright these supernovae appeared to how bright they should be, the teams could calculate precisely how far away they were, and by measuring their redshift, how fast they were moving away from us. What they found changed everything. The distant supernova were fainter than expected, which meant they were farther away than they should be. If the universe's expansion were slowing down instead of decelerating, the expansion of the universe was actually accelerating, speeding up, not slowing down. It was as if that ball thrown upward had suddenly decided to fly faster and faster into the sky, defying everything we thought we knew about gravity. This discovery earned the 2011 Nobel Prize in Physics, but it also created one of the deepest mysteries in modern science. What could possibly be causing the universe to expand at an accelerating rate? The answer, or at least the name we've given to our ignorance, is dark energy. But calling it dark energy is a bit like calling an unknown sound in your attic a mystery noise. It's a placeholder, a confession that we don't really know what's going on. Dark energy appears to make up roughly 68% of all the energy in the universe. That's more than twice as much as all the ordinary matter stars, planets, galaxies, and cosmic dust combined. And yet we have no idea what it actually is. It doesn't emit light, it doesn't absorb light, and it doesn't seem to interact with matter in any way we can detect directly. We know it exists only through its effect on the expansion of space itself. Imagine trying to understand a symphony while being completely deaf to most of the instruments. That's essentially where we stand. With dark energy, we can see its effects, the accelerating expansion, the way it influences the large-scale structure of the universe, but the thing itself remains tantalizingly out of reach, like trying to study a ghost by watching doors open and close. The most straightforward explanation for dark energy draws from Einstein's general theory of relativity back in 1917, when Einstein first formulated his equations describing gravity and space-time. He noticed something troubling. His equations suggested that the universe should either be expanding or contracting. It couldn't remain static. But at the time, everyone believed the universe was eternal and unchanging. So Einstein added what he called the cosmological constant, a kind of anti-gravity force that would exactly balance the attractive pull of gravity, keeping the universe stable. When Hubble later discovered that the universe was indeed expanding, Einstein famously called the cosmological constant his greatest blunder. But perhaps it wasn't a blunder after all. Perhaps Einstein had accidentally discovered dark energy decades before anyone knew the universe's expansion was accelerating. The cosmological constant, in modern terms, represents the energy of empty space itself. According to quantum mechanics, even empty vacuum is not truly empty. It seethes with quantum fluctuations, virtual particles popping in and out of existence in the briefest of moments. If these quantum fluctuations contribute to the energy of space, and if energy and mass are equivalent, as Einstein showed us, then empty space itself should have a kind of weight. That weight would manifest as a repulsive force pushing space apart faster and faster, exactly what we observe with dark energy. The problem is when physicists try to calculate how much energy empty space should have based on quantum mechanics, they get an answer that's larger than the observed value by a factor of 10 to the power of 120. To put that in perspective, imagine trying to measure the width of a human hair and being off by more than the distance to the edge of the observable universe. It's not just wrong, it's spectacularly, catastrophically wrong. This discrepancy between theory and observation has been called the worst prediction in the history of physics, and yet the cosmological constant remains one of our best explanations for dark energy, simply because we have so few alternatives. Another possibility is that dark energy isn't constant at all, but rather a dynamic field that changes over time. Physicists call this hypothetical field quintessence, after the fifth element of ancient Greek philosophy. Unlike the cosmological constant, which would remain perfectly uniform throughout space and time, quintessence could vary from place to place, and epoch to epoch. It might be stronger now than it was in the early universe, or it might be growing stronger still. If dark energy is indeed quintessence, it opens up fascinating and slightly unsettling possibilities. The expansion of the universe might not just continue to accelerate, it might accelerate faster and faster, leading to what cosmologists cheerfully call the Big Rip. In this scenario, dark energy would eventually overcome not just gravity on cosmic scales, but all the fundamental forces that hold matter together. First, galaxies would be torn apart, then solar systems, then planets, and eventually even atoms themselves would be ripped to shreds by the expanding space between their components. But before you start writing, your cosmic will consider that this fate, if it occurs at all, lies trillions of years in the future, plenty of time for civilizations to rise and fall, for stars to be born and die, and for the universe to tell countless more stories. There's also the possibility that we're thinking about this entirely wrong. Perhaps dark energy isn't a new form of energy at all, but rather a sign that our understanding of gravity itself is incomplete. Maybe Einstein's general relativity, while extraordinarily successful in describing gravity on the scale of planets and stars, begins to break down when applied to the entire universe. Some physicists have proposed modified theories of gravity that could explain the accelerating expansion without invoking dark energy at all. These theories suggest that gravity behaves differently on the largest scales, becoming repulsive rather than attractive when applied to cosmic distances. It's a radical idea that would require rewriting textbooks, but science has a history of radical revisions. What makes dark energy particularly mysterious is how perfectly tuned it seems to be. If dark energy were much stronger, the universe would have expanded so rapidly in its early history that galaxies and stars would never have formed if it were much weaker. Gravity would have won out long ago, and the universe would have collapsed back in on itself in a big crunch. Instead, we find ourselves in a universe where dark energy and matter are almost perfectly balanced, allowing for billions of years of cosmic evolution. This apparent fine-tuning has led some scientists to speculate that we might live in a multiverse, a vast ensemble of universes, each with different amounts of dark energy. Most of these universes would be sterile, unable to form the complex structures necessary for life. But in a tiny fraction like ours, the balance would be just right for stars, galaxies, and eventually living beings to emerge. We observe the universe we do precisely because we exist to observe it. The implications of dark energy extend far beyond academic curiosity. If the acceleration continues, and current evidence suggests it will, the universe faces a lonely future. As space expands, galaxies, not gravitationally bound to our local group, will recede beyond our cosmic horizon, their light red-shifted into invisibility. The night sky will gradually empty, leaving only the stars of our own galaxy and its immediate neighbors. Even within our galaxy, the raw materials for star formation will eventually be exhausted. Without the infall of fresh gas from intergalactic space, star birth will slow and finally cease. The universe will enter what cosmologists call the stelliferous era's end, when the last stars burn out, leaving behind only white dwarfs, neutron stars, and black holes slowly cooling in an ever-expanding cosmos. Yet even this isn't the end. Black holes themselves will eventually evaporate through Hawking radiation, returning their mass to the universe as elementary particles and thermal energy. The timescales are almost incomprehensibly vast. The most massive black holes will take longer to evaporate than the current age of the universe, multiplied by trillions of trillions. But eventually, even they will fade, leaving behind only a thin soup of particles, growing ever more dilute as space continues to expand. This ultimate fate, known as the heat death of the universe, represents a state of maximum entropy where no further work can be extracted from the cosmos. It's a future so distant that it makes the extinction of the dinosaurs seem like yesterday. But it's also a reminder of how precious and temporary our current cosmic moment truly is. For now, though, dark energy remains one of the universe's greatest puzzles. We can measure its effects with increasing precision. Space telescopes and ground-based surveys are mapping the expansion history of the universe in unprecedented detail, but the fundamental nature of this cosmic accelerator continues to elude us. Perhaps future generations will look back on our current confusion about dark energy the way we now view the pre-Copernican belief that Earth was the center of the universe, an understandable misconception based on limited observations. Maybe the answer will turn out to be surprisingly simple once we have the right theoretical framework, or perhaps dark energy will remain mysterious, challenging our understanding of physics for centuries to come. What we do know is that dark energy has fundamentally changed our picture of the cosmos we live in, a universe dominated not by matter and radiation, but by something far stranger, a force that pushes rather than pulls, that creates rather than destroys distance between objects. It's a universe that's not just expanding, but accelerating away from us in all directions, like the surface of a balloon being inflated by an invisible and inexhaustible breath. And here we are, conscious beings made of ordinary matter, floating on a small planet around an ordinary star in an ordinary galaxy, trying to comprehend this extraordinary cosmic acceleration. We are the universe becoming aware of itself, puzzling over its own expansion, measuring its own acceleration with instruments made from its own atoms. As you drift towards sleep, tonight consider that you are quite literally along for the ride on this cosmic journey. Every breath you take happens in an expanding universe. Every heartbeat occurs as space itself grows larger around you. The very atoms in your body forged in the hearts of ancient stars are being carried along by this mysterious dark energy toward a future we can barely imagine. So rest well, fellow cosmic traveler in a universe that's racing away from itself. You found a moment of stillness, a quiet pause in the grand acceleration, and perhaps that's enough for now. Sweet dreams in the expanding cosmos. And so here we are, gently floating back from the far reaches of space and time, having journeyed through the birth of galaxies and the mysteries of dark energy. We've drifted alongside ancient light, watched stars ignite from primordial clouds, and witnessed the grand cosmic dance that shapes our universe. Along the way, we've discovered that expansion isn't slowing down, it's speeding up, pushed by something we're only beginning to understand. What started as tiny ripples in the fabric of space-time has blossomed into the magnificent cosmic web we see today, with galaxies spinning like islands of light in an ever-expanding sea. And perhaps most remarkably, we've learned that this acceleration means our universe's story is far from over. It's entering a new chapter, one where space itself becomes the main character. So as you drift off to sleep tonight, remember that you're not just resting on a small planet orbiting an ordinary star. You're riding along on one of the most extraordinary adventures the cosmos has ever undertaken, carried by the very expansion of space itself into an infinite and beautifully uncertain future.